Hi, my name is Chike Abua, and I'm going to be talking about Solo, which is a lightweight static analysis for differential privacy. For this talk, I'm going to assume the listener has some idea of what differential privacy is. It usually involves addition of random noise to some query output, or adding random bias to some selection algorithm. The amount of noise we add depends on the sensitivity of the algorithm being made private. In general, we would like to perform verification of private algorithms to remove the risk of non-experts making mistakes in privacy analysis. The related work for this includes fuzz, which is a static analysis via linear types, and dpello, which is a static analysis via symbolic interpretation of the program AST. Solo performs a static analysis of differential privacy, which occurs in tandem with the GHC Haskell compiler, type checking the program. The program will receive regular Haskell type errors when their program violates privacy, and a privacy budget estimate along with the final types of their functions and programs. Our approach makes use of the idea that a static privacy analysis of a program can be centered around a set of sensitive data sources which the analyst wants to preserve privacy for. A data source may be represented by some identifier such as a string value, which represents some sensitive program input such as raw numeric data, a file, or an I/O stream. Solo's data sources are inspired by ideas from static taint analysis. We taint the program's data sources with sensitivity annotations that are tracked and modified throughout type checking. To enable the static privacy analysis of a program, we track privacy information for data sources at the type level. Because our analysis is based on the information flow of distinguished data source values throughout a program, we are able to perform a fully static analysis without precise tracking of variable usage within functions, and without a specialized linear type system. In Solo, data sources are created for sensitive inputs external to the program. For example, the read double from I/O function reads in a sensitive double value from the user. Sensitive values whose types are prefixed with S, such as S double, represent base values that have been tagged with sensitivity tracking information. Read double from I/O instantiates the sensitivity environment to O1, which indicates that values with this type are 1 sensitive with respect to the input read from the sensitive source O. The distance metric identifier M specifies the metric used to measure distance. Sensitive values like S double are encapsulated in order to restrict their usage to only privacy-preserving operations. The constructors of sensitive data types are hidden, and they are manipulated solely through trusted primitive operations. We can use the Laplace and Gaussian mechanisms to add noise to sensitive values and satisfy differential privacy. Solo tracks the privacy cost of multiple uses of these mechanisms using a privacy monad, which is similar to the one used in fuzz and in related systems. The following function, simple privacy function, takes in S double as input, doubles it, and adds noise. The type of the function indicates that the function satisfies epsilon differential privacy for epsilon equal to 2. Haskell is able to infer the type of the function if the annotation is left off. Alright, the approach used in Solo to bound function sensitivity is to write function types that are polymorphic over sensitivity environments. In general, we can recover the notion of an S-sensitive function in Solo by writing a Haskell function type that scales the sensitivity environment of its input by a scalar S. The common case of a one-sensitive or linear function can be represented by keeping the input sensitivity environment unchanged. The map primitive describes a computation that accepts as inputs an S-sensitive unary function from values of type A to values of type B, and the list of values of type A. Map returns a list of values of type B, which is S-sensitive in the former list. Alright, privacy environments track a privacy cost associated with each data source. Privacy environments for pure epsilon differential privacy are defined as seen here. TLRAT is a type-level encoding of positive rational numbers by a pair of the numerator and denominator as natural numbers in GCD reduced form. The sequential composition theorem for differential privacy provides the basis for the definition of a privacy monad. We observe that our privacy environments have a monoidal structure, and we derive a privacy monad which is indexed by our privacy environments. In the same style as a notion of effectful monads or parametric effect monads given separately by Orchard and Katsumata. Computations of type privacy monad are constructed via the core, return, and bind functions. The return operation accepts some value and embeds it in the privacy monad without causing any side effects. The bind operation allows us to sequence private computations using differential privacy's sequential composition property, encoded here as the type family epsecomp. In the computation bind fg, we execute the first private computation f for some polymorphic privacy cost p1, pass its result to the second private computation g, which executes for some privacy cost p2, and output the result of g at a total privacy cost of the degradation of the p1 and p2 privacy environments combined according to sequential composition. Okay, finally I'd like to talk about one of our case studies, gradient descent, implemented here as the function gd. As inputs, the GD algorithm accepts a list of feature vectors x's representing sensitive user data, a set of corresponding classifier labels y's, a number of iterations to run k, and the desired privacy cost per iteration epsilon. The algorithm works by moving the current model in the opposite direction of the gradient of the loss function. In order to preserve privacy for this function, we may introduce noise at the point where user data is exposed, the gradient calculation. The let-bound function f in the GD algorithm contains the workload of a single iteration of the program, in which we perform the gradient calculation and introduce noise using the vector-based Laplacian mechanism. Alright then, thank you very much for listening, and the full paper can be found on my website.